So in this problem here, we have a 1,200 kilogram car that's traveling due towards a deer on a horizontal plane, traveling at 105 kilometers per hour, and then it reaches a standstill resting point of 0 kilometers an hour. We are asked, what is the net amount of work done by the car to stop itself to 0 kilometers an hour? So we know that work net is equal to, and that's going to be equal to the change in kinetic energy plus the change, that's not a delta sign, change in potential energy. So that's the relationship we have, right? Pretty simple. And let's just look at this qualitatively, because this is going to be the equation we use. We're not going to use that work is equal to the parallel force times the distance, right? We don't have any of that information. We only have this. So, kinetic energy, potential energy. Are we changing our potential energy? Okay, so as we go from 105 kilometers to 0 kilometers, are we gaining any potential energy, i.e. energy based on position? Well, you would say no, right? Because our position, although it's changing in the x direction, we know that potential energy is equal to mass, gravity, height. The mass of the object stays constant. Gravity is always 9.8 meters a second towards the center of the Earth, or in this case, down, right? Not in the horizontal region. And it's based on the height of which you are from the ground, right? So we're 0 meters from the ground, therefore height doesn't change here, right? We're 0 here, we're 0 right before we hit the deer, or if we hit the deer, I don't know. We're assuming that he got frightened and he's hitting his brakes really hard so he doesn't hit the deer. We're not asked, oh, is he gonna hit the deer? We're just asking, okay, he's slowing down to 0 kilometers an hour. How much work does that take? Anyways, moving on. His height does not change. He does not just magically float in the air, right? His position does change in the x-coordinate, not in the y. So for that reason, change in potential energy drops out of the equation. We're left with that the work net is equal to delta KE, which is kinetic energy. So what is kinetic energy? Kinetic energy is equal to 1/2 the mass times the velocity squared. Okay, pretty simple. It just tells you what is the energy in joules of a something in its motion, right? Pretty simple. How much work can it do based off its movement? So, the energy of its movement. So we know that if we want to find the change in potential energy, we need to take the kinetic energy at its final point, which is 0 kilometers an hour, and then subtract it by the kinetic energy of its initial, right? So the initial kinetic energy is what we're subtracting from the final kinetic energy. That will give you the change in kinetic energy. So we can actually plug this in. That work net is equal to kinetic energy final is 1/2 mass velocity squared. We'll put an F to signify that it is the final velocity. We're going to subtract that from 1/2 mass velocity initial squared, and that will give us the work net. Notice one thing that we can do here that's pretty important. If you know from algebra, we can factor things out, right? If I have some term x plus y, and I put a 3 in front of it, so a little ugly there, sorry, 3x plus 3y, well, this is the same as saying, if I were to bring the 3 out front, 3 times x plus y, right? If I were to distribute the 3 right back in, we'd get this equation up top. And that's exactly what we can do with our equation here if we factor out a mass and a 1/2. So we will say that the work net is equal to 1/2 mass, because that stays constant, right? Velocity final squared minus velocity initial squared. These are not constant. These are different values. We can't just factor out a velocity here. Okay, so we have that the work net is equal to 1/2 mass velocity final squared minus velocity initial squared. Okay, before we plug and chug, it's really important that you see the units of work. Work is described in joules, okay? A joule is equal to a Newton meter. What is a Newton meter? Well, it's a Newton times a meter, so a Newton is equal to a kilogram times a meter over the reciprocal seconds squared. We're going to times that by meters, okay? Kilograms, meters, seconds to the negative second, okay? This simplifies to kilograms meters squared per second, right there. Okay, so our units need to match this when we are simplifying, right? So if you think about it, mass is in kilograms already, we're given that, but our velocity is not. It's given in kilometers per hour. It should be in meters per second. So let's do the conversion. And I'll actually change colors. 105 kmh. Okay, so you can actually rewrite this to make it a little easier to visualize if you put hours on the bottom here. So let's actually change our kilometers first. So what you do is you say, okay, you know that 1 kilometer is equal to 1,000 meters. Pretty simple. And that will give us meters per hour. And let me grab my calculator. Okay, 105 times 1,000. We know that we're going to travel roughly 105,000 meters per hour. Okay, so, and I'm just fully explaining the dimensional analysis because when you look at these online problems, sometimes there's just things that you get confused about that the person that's doing the problem doesn't explain. This is why I do this per hour. So we know that 1 hour, okay, is equal to 60 minutes. All right, 60 minutes, how many times is in a second? 60 times 60, 3,600 seconds per hour. Okay, so notice how these units will cancel, and we're going to get meters over seconds. So let's actually do that now. Divided by 3,600, we get that the car is moving at 29.17 meters per second. And we can keep 3 sig figs, so I'll actually round this to 29.2 meters a second. Okay, so that's how fast we're moving. Now we're ready to plug and chug, right? We know that this will just be 0 meters a second. That's just 29.2. So the work net is equal to 1/2 mass, 1,200 kilograms. Velocity final squared is 0. 0 squared is 0. So we'll say 0 minus 29.2 squared, which is 852.6 meters squared seconds to the negative 2. Okay, now let's just do a simplifying step here to get our final answer. Negative 852.6. Okay, so we get that the amount of work that we need to do is approximately equal to 511,560 joules. We can convert this to kilojoules by dividing by 1,000. So negative 512 kilojoules. Or you could say that this is also equal to negative 511,560 Newton meters. I hope you guys enjoy them. Again, those are all equivalent. Let me just, sorry, I cut off the screen a little bit. There's all the work for this here. Quite a simple problem, but sometimes, you know, when I'm lecturing, I like to give the full explanation down to every little detail. You know, it is extensive, but if you know something, you'll just skip right through it, and that's okay. Hope you guys enjoyed. If you have any questions, put them in the comments if I missed anything. Have a wonderful day.